Hello everyone, my talk is called Heroes of Myth and Magic Free in the Browser. Is it hard or not? I've been working on porting games since 2012. The first project I brought to the browser were OpenDune, Open Transport Tycoon, and OpenXCOM, all well-known classic retro games. After that, I joined GamePix company, where I work professionally on porting games. Since 2012, our team has ported over 100 different games and engines to the browser. I'm also an active contributor to the Emscripten and Binarium projects. But that is not all. I am the author of the JS-DOS library, which lets you run DOS and Windows games in the browser. This library has a community portal called DOSZone, where you can find many classic and popular games. You can play them in the browser for free. Today, there is no more debate about whether something can be ported to the browser. It is clearly possible. That has already been proved. But a new question appears. Is it hard or not? Maybe you have a cool project and want to run it in the browser, but don't know how long it may take. This is a question we will try to answer today. I'll first give you a short history of porting, then show a simple example, then a complex one, and finally we will talk about heroes of Media Magic Free. So everything starts with the fact that you have a cool C++ project and want to run it in the browser. If we go back in time, there was no real way to do this. The only option was to rewrite everything from C++ to JavaScript, which is extremely hard. C++ is a complex language, and rewriting it in a totally different language is very difficult. That is why in 2010, Alon Zakai came up with an idea how to port complex C++ project to the browser. He suggested using a C++ compiler clang. More specialty its ability to generate LLVM bytecode. This means no matter how complex your project is, Clang turns it into simple and understandable LLVM bytecode. Then you use a compiler called EMCC, part of Emscripten, to convert that bytecode into JavaScript. This task is much easier and it was implemented pretty fast. Soon after first version of EMCC came out, large projects like SQLite, DOSBox, Doom were ported to the browser. But the problem was that these JavaScript versions were much slower than the native C++ ones. So Emscripten developers introduced a new standard, AsmJS. It's still JavaScript, but written in a special way that browsers can optimize well. This helped many projects run reasonably fast, and real browser-based apps began to appear. But industry didn't stop there. They created a new standard, WebAssembly. Today it is a default choice for running Bing apps in the browser. Over the last 10 years, the tech has come a long way, and now programs running in WASM often have a performance close to native. To show this progress, here is a short video. Back in 2012, I ported DOSBox to the browser and ran the game Command & Conquer on the left side. But I couldn't play it. I had to wait 10 minutes just to see the game menu. Today, if you run the same game in the browser, you actually need to go into the settings and set the game speed to minimum. Otherwise, it runs way too fast. That is how big progress is. So, the question isn't whether you can port something to the browser. We know you can. The real question is this hard or not. Let's look at the first example, a classic cult game called Vangers, released in 1998 by Studio Cadelab. It's still considered a cult hit. The code was written without any abstractions, using a lot of complex math and logic. The code is very hard to read and understand. Editing it directly in C++ is extremely difficult. But for us, that does not matter. We don't plan to modify the code. We just want to check how hard it to port. We can start by looking at the key characteristics of the game. First, the operation system. This is important because Emscripten was created as drop-in replacement for the GCC compiler. The idea was simple. You take a program that normally compiles with GCC, replace GCC command with MCC, and it compiles for the web. Based on this idea, Emscripten evolved and added full POSIX support for Unix-like system. It also includes many Linux libraries like OpenGL, Petred, and more. So, if your game is built for Windows, that is a bad sign, because EMCC doesn't support any Windows API. None of them will work, and you'll need to replace them with open source or POSIX compatible libraries. macOS is much better, since it is a POSIX compatible platform. If your C++ project runs on macOS, that's a very good sign for porting. Mobile platforms are usually a bad sign. If the project is written in native mobile languages like Java, Kotlin, or Objective-C, it won't work, and you'll have to rewrite everything. But if it's written in C++, that's actually great because Android is based on Linux, and Linux is the best system for porting. Vangers today is a cross-platform project, it runs everywhere, so in this case it gets a green light. Next is the game engine. If your game is written in a language supported by WebAssembly, that is great. There are many such languages: C++, C, Go, Rust, Zig, and others. Of course, if you are using a modern engine like Unity, Godot, Cocos, or any similar one, that is also great, because they all support export to the browser. But if you are using something else, then right now you probably have no direct options. The only path may be emulation. For example, for Flash you can use Raffle, which works very well. For DOS there is JS-DOS. That is a direction worth considering. In the case of Vangers, it is written in C++, so everything looks great here. Next, we look at the libraries that project uses. Obviously, if it uses open source libraries, that is a very good sign. Almost all popular open libraries try to support WebAssembly out of the box. In fact, Emscripten has a project called Emscripten Ports. It adds many popular libraries directly into Emscripten. So all the libraries shown on the slide can be enabled with a single command and will work right away. Vangers uses SDL, the most popular library for games, and all its versions work out of the box. Next we have a content, the parts users interact with: models, story, art, and others. This content is usually stored in files, and the way the game accesses these files affects difficulty of porting. The ideal case is when the game uses standard C++ file API, like streams, fopen, fclose. With this, everything works out of the box. Emscripten emulates a virtual file system in memory by default. But with one flag, you can switch to storing the file system in indexed.db, so your changes persist between sessions in the browser. There is also support for asynchronous file systems, and you can always write your own logic in JS based on how Emscripten works. But if your project uses a custom format like VAT files in Doom, then you can't rely on any of the built-in solutions. Vangers uses the standard file library plus a Huffman compression algorithm, which is not ideal. If you look at the world of Vangers, it's basically a collection of images that are rendered together to create the final map. All these images are packed into a single file, which is about 60 megabytes. Then a Huffman compression algorithm is applied, and the result is 22 megabytes file. It seems like a win, less data to download. But in practice, the browser needs to download that file and store it in memory. Then it has to decompress it using WebAssembly code, and that happens in the main thread, which can block the browser. After decompression, it also needs to allocate 60 MB of memory for the final result. If the game had used the uncompressed file instead, we could apply a better trick, server-side compression. For example, using the Brotli algorithm. Brotli compresses better than Huffman, and it's supported by browser. The browser will then decompress the data on the fly while downloading, without needing extra temporary memory. It also uses native libraries built in the browser, which is much faster and doesn't block the main thread. At the end, we still need to allocate memory for the final file, but the process is smoother and more efficient. So, in the end, using uncompressed resources means faster network transfers, less memory usage, and no blocking of the main thread. That's why it is better to work with uncompressed data in that case. In any game, rendering is an important part, but in Vangers, the rendering is just C++ code, which means Emscripten can port it as is with no issues. No exceptions in the code, no problem. No threads, also no problem. Now let's look at the heart of any game. It's game logic. I call this loop system. As we know, browsers don't allow infinite loops. If I write a function with an infinite loop that tries to print something to the screen and run it in a tab, the tab will freeze or crash. This is a serious limitation for native programs. But in Vangers, this part is well designed. Each game logic iteration is broken into quants. Quants are small, separate units, each responsible for something. One for sound, one for physics, one for AI, and so on. So a single logic step is set of these small quants, and it always ends. That is how it should be done. If your project different, for example in OpenDune, things get harder. It uses an infinite loop that waits for the game state to change. That loop is inside another infinite loop that waits for keyboard input. But keyboard input can't be processed because the browser is waiting for JS frame to finish, so everything hangs. In that case, you'll need to rewrite the logic to use a quant model or something similar. Once you rewrite it, and you have a function that handles one step of the game loop, you just call Emscripten setMainLoop and pass that function. Emscripten handles the rest. It registers the function with request animation frame and runs it at the right frame rate. Sometimes rewriting infinite loops isn't realistic, like with OpenDune, where the whole game is built around them. Rewriting everything will take too much time. In such case, Emscripten has a feature called Asyncsify. It automatically transforms infinite loops into resumable code, but it comes with a performance cost. It can be slow at runtime. In Vangers, the loops are implemented as a quants, so everything works well. Another simple characteristic of any project is its size. If your game is under 10 megabytes, that's excellent. It matches the size of typical large WebAssembly projects today. In general, if the game is under 100 megabytes, that is still acceptable. With a good CDN, it will load in about a minute, and if the game is good, user may be willing to wait. But anything larger is a problem. Transferring big data is expensive, and most users won't wait for huge downloads to finish. Vangers is about 500 megabytes, which is a lot, but we applied a trick. We found the point where the game loads its resources and added a flag to pause loading. Emscripten has a function called Emscripten async It lets you specify a URL to download a file and where to place it. Once the download finishes, a callback is triggered, and we resume loading. This simple trick helps reduce the initial download size and makes the game feel lighter for users. Some of the most visually impressive parts of games often involve video, but video is heavy resource. It takes up a lot of space, and decoding it on CPU is very resource intensive. So if you see video in a game, the first thing you should ask is, can it be removed? If yes, do it and come back to it later. If the video must stay, one good option is to use the HTML video tag. This is a perfect solution for cutscenes. It's easy to implement, and the browser starts playing the video before the full file is downloaded. It also supports modern codecs that compresses video very well, so even big files are manageable. But video is not perfect solution. It is asynchronous, and that can create problems. For example, in one game we worked on, characters had static sprite bodies, but their heads were rendered using video. When we switched to using the video tag, the body appeared first and the head was missing, just empty space. Then the head appeared. Then animation changed and again no head. Head appears, head disappears. It looked weird. So in some cases video tag can't be applied. If video tag doesn't work, you need to see if the code can be rewritten or adapted. In Vangers, we replaced the video with GIF images and that worked great. And if nothing else helps, you can always use FFmpeg to decode video in WebAssembly. It will be slow, but it will work. The audio system is probably the simplest part of any game. Most modern libraries support Emscripten out of the box. And if something doesn't work, you can always disable sound as last resort. In general, audio causes the fewest problems when porting. But sometimes there are special cases. I call them dynamic audio system. This generates sound in real time using the CPU. For example, in Vangers, the buzzing of fly swarms, the sounds of whirlpools, landslides, and engines all are calculated on the fly. In the browser, this can be slow. It is better to replace such sound with static audio files, like we did, and everything was fine. Today, most people access browser games from mobile devices, so important to check whether the game supports mobile platform. That means handling tall screen resolutions and touch controls. In Vangers there was none of this, so we had to put in quite a bit of work to implement touch controls, and that was fairly difficult. To sum it up, for Vangers most things are in green zone with just few yellow areas, so we can say that porting this game to the browser was fairly easy, and that is exactly what happened. We made a beta version in just 2 weeks, and most importantly, it ran without any errors in the browser right away. Now let's look at the opposite example, the legendary Russian strategy game Perimeter from the same studio. It is a much more modern game. It uses a powerful graphics stack with shadows, reflections, and even terrain deformation. It is written in a modern OOP style with lot of math, and it is a very large project. If we look at final evaluation table, things don't look great. On the positive side, the engine is written in C++, the game logic is based on quants, and there are no exceptions in the code. But the bad part is the entire project is built for Windows and it uses WinAPI. As I mentioned earlier, none of that works with Emscripten, so all of it would need to be rewritten. But the biggest problem with the game, it is a powerful 3D engine. It is built on DirectX, which is a closed Microsoft-only technology. There is currently no way to automatically convert DirectX to WebGL or WebGPU. Maybe someday that will change, but for now it is not possible. So you have to rewrite all DirectX code to use WebGL. If you are going to do that, it's better to switch to an abstraction library like Sokol, BGFX or something similar. That way you solve several problems at once. Your game become cross-platform and will also work in the browser. However, every new abstraction layer introduces its own bugs. When we did the rewrite, we found two rendering bugs, and once you finally get it all running in the browser, you will discover something ironic. Most browser uses Google Engine library, which translates WebGL back into DirectX under the hood. To sum up, any abstract graphics API is great, using GLES 2 is great, OpenGL Legacy is worse, but not a deal breaker. It doesn't translate automatically, but there is a library called Regal that helps. It is not perfect, but sometimes it works. For example, Unreal Tournament 99 was ported to the browser using Regal, and it works well. In the end, OpenGL Legacy is a simpler graphics stack, so you can usually rewrite it to GLES 2 without too much pain. But if your game uses Metal, DirectX, Vulkan or OpenGL 4, that is bad news. There are more powerful graphics API and rewriting them to GLES is very hard, especially if the game has advanced visuals. This is one of the biggest problems today. Perimeter uses DirectX. Another important aspect of this game is memory usage. Based on our testing, we found that on desktop browsers you can use around 2 GB of RAM per tab and still run stably. On Android, you have about 1 GB to work fine. But on iPhone, the limit is near 500 megabytes, and if you go over that, the browser may force close the tab. In WebAssembly, memory is just a byte array. When it runs out, a larger buffer is allocated and everything is copied. This causes a memory spike, so it is very important to estimate memory usage early and allocate enough from the start. Also, memory is used to store the file system, so if your game needs 256 megabytes of RAM and your resources take another 256 megabytes, you are already entering the critical zone. Perimeter fits in 512 megabytes, which is good, but not ideal. Another common issue with Windows is that developers often ignore file name case sensitive. Because Windows has a case insensitive file system, so projects may compile fine but then fail at runtime. Because a file is named with one case on disk and referenced with a different one in the code. On POSIX systems this doesn't work, file names must match exactly. To fix this, the simplest way is to convert all file names to lowercase and follow that rule consistently. In Perimeter we solved it differently. At startup we scan the virtual file system and build a file index. When the program requests a file, we look the correct path from that index. This solves the case mismatch issue. Another very interesting feature of this game is that it supports multiplayer, but in a networked match, each client runs its own game logic and over time they start to desync. In the end, each client might think it's winning. Why does this happen? Here is a simple example. Imagine you have two numbers, you multiply them and print the result, along with their byte representation. If you compile this program on Ubuntu and also to WebAssembly and run both versions, the text output may look the same, but the byte output may be different. That is because the floating point math standard doesn't guarantee determinism. This means if you compile the same program on different devices, there is no guarantee that the same input will give the same output. Worse, even compiling the same code multiple times on the same computer can lead to different results between builds. In-game, this causes real problems. For example, a turret receives soldier positions from the server. It runs its algorithm to prioritize targets as 1, 2, 3. But on another client due to non-deterministic math, the same logic with the same data may give a different results. So it picks a different target. Over time, clients fall out of sync and the game state no longer matches. There are two main solutions. Use deterministic math libraries like GateMath. Or, if you are targeting only WebAssembly, you are lucky. The WASM standard guarantees deterministic math, so as long as you are not mixing systems like WASM and native, everything will stay in sync. Another big issue with this game is its size. It takes up to 4 gigabytes. No one is going to wait for a 4 gigabytes download just to try the game. Emscripten has a solution for this: asynchronous file systems. The idea is simple. The game starts without files. When the file is needed, the game pauses, downloads the file, and then resumes until the next file is needed. Unfortunately, this doesn't work well for perimeter, because the game has around 5,000 files and it loads something every second. For example, building a new soldier loads their model, scrolling the map loads textures. This constant stopping and loading makes the game unplayable. Still, despite all this, the game does work in the browser. Everything is solvable. So, if you look at all of this, it is clear that Perimeter probably wasn't the best choice for porting. It was going to be very difficult, but we really love this game. It had a strong community, and we decided to work on it anyway. Interestingly, parts like the rendering engine and network code were rewritten by a fan of the game from Basque country, which has personally impressed me a lot. Yes, it took us about a year to port the game, but we made it work, and recently we even added shadows and reflections, so it's already the second year of the project, but it works in a browser great. Now let's move on to the famous game Heroes of Myth and Magic 3. I think everyone knows and loves it across the world. As soon as I found there was an open source implementation of the game, I decided to port it to the browser. The project is called VCMI. It is well known and has been around for a long time. I can say that the code quality is excellent. It uses OOP properly, only open source libraries, and has a friendly community. It is a really solid project. I highly recommend it to everyone. And if we look at the overall evaluation table, things actually look very good. The project uses open source libraries, and the only minor issue is a custom file system, similar to VAD files, but it is not a big deal. In theory, this game should work out of the box, and in fact it does compile with minimal changes and even launches in the browser, but doesn't work. There are two main reasons for that: networking and multithreading. In general, networking in Emscripten works great, as long as your project uses standard POSIX sockets and dedicated game server that communicates over normal TCP/IP. In that case, everything works out of the box. When you compile your project with Emscripten, it replaces POSIX sockets with a WebSocket and wraps your binary data in WebSocket messages. The only thing you need is a special proxy, like WebSockify, which converts WebSocket messages back into regular TCP/IP streams. You don't even need to change your server, it just works. We have tested this on many games. But this doesn't work for VCMI. The reason is that in VCMI, the client and server are the same program. When you start a game, even in single player, the client tries to locally create a server and open a port. But browser can't open ports, so the process crashes right there. But if you connect to a remote host, everything works fine. But because even single player tries to spin up a local server and the browser can't open the port, the game just doesn't start. That is the real reason why VCMI didn't work in browser out of the box. To solve this problem, I wrote a local dummy server, one that doesn't open any ports. It just acts as a placeholder and bounces all requests back to the client. I thought, great, now it should work, but still didn't. Why? Because game is multi-thread. The client sets a mutex when it makes a request to the server, and the server also sets a mutex when it responds. But now, since the client and the fake server are running in the same thread, this all ends up in a deadlock. At first I tried to fix it using recursive mutexes, but I eventually realized that there is no way to remove multi-threading from the game. It is deeply integrated. I started running my local server in a separate thread, and yes, that's finally working. The game could now create maps, and you could even take a few turns before it eventually froze again. The game freezes because multi-threading is a very complex topic. When you switch from native threading to something else like the browser's threading model, it introduces many new bugs. But first, to even enable multi-threading in the browser, you need to set up a CoAP context. And setting that up is not easy. Plus, once your page uses CoAP, it cannot load resources from other servers that don't support it. This means things like authorization, monetization, and analytics will break on that page. In short, if your project uses threads, you can basically forget about any commercial web version. A great example of this is the Godot game engine. In version 4, they focused heavily on multi-threading, thinking it will take off, but it didn't. Many users reported they couldn't upload their games to major platforms, so in version 4.3, Godot removed the threading requirement and now it is possible to build games without it again. But since our project isn't commercial and we don't care about monetization, we can move on the technical challenges. Multi-threading in browser is very different from what we use on the desktop. It is based on forking model, meaning each new thread is actually a separate worker, which is a copy of your entire program. So if your app spawns 24 threads, the browser creates 24 workers, each holding a copy of your code. They communicate using message, which can be slow. Also, browsers have limits on how many workers can be created. In Chrome, if you spawn too many, like game does, uh, the tab can crash. In Firefox, the number of workers is controlled by config settings, and the default is quite low, only a few dozen. That is a problem, because native program often create hundreds of threads, and everything works fine. In the browser, this approach just doesn't scale. That is the first limitation, and here comes the second. In the browser, we can block the main thread, but the game does that very often. For example, the game frequently parallelizes operations. One case is upscaling images. It uses all low-level resolution assets, and depending on image size, it splits them into 16 or 4 parts. Then it spawns 16 or 4 threads, each upscaling a part of the image. The main threads then waits for the workers to finish before continuing. But in the browser this doesn't work, because if the main thread is blocking, it can't send or receive messages, and that leads to a deadlock. Thankfully, the game uses a popular library thread building blocks, TBB, and with some minimal effort we were able to replace its implementation with our own. The trick we used was simple. If we are on the main thread, we don't parallelize, we just run the task directly. If we are on a worker, we allow parallel execution, but only if no other worker is already parallelizing. and we limit it to maximum of 4 threads. This workaround helps avoid flooding the browser with workers and solves the worker limit problem I mentioned earlier. After those changes, the game started to work quite well, it became mostly playable, and we moved on the publishing stage. One more thing to know. File systems in the multi-threaded browser version work a bit differently than in a native environment. In the browser, the file system is stored in the main thread, which has a direct access with no delays. But workers don't have that access. If worker want to read or write a file, it must send a message to the main thread, which then performs this operation. That means all file operations in workers have a bit of delay. This can lead to issue, though in practice this problem rarely show up. Still, it is important to be aware of this behavior when working with multi-threaded code in the browser. Also, multi-threading does not work in WebView, and this is well documented. In the official Android WebView docs, you will see that shared array buffer cannot be created. So, for example, if someone shares a link to your game in Telegram and opens it inside the app, it won't work because WebView blocks multi-threaded features. It, it is the same on iPhone with iOS less than 18.2. Safari has a bug that prevents creation of shared array buffer, and that is not even very old OS version. Not all libraries and Emscripten ports support multithreading either. For example, libpng can't be compiled in multithreaded mode, so we had to throw it out and replace it with STB images. Also, POSIX signals aren't supported. Just for reference, it's rarely used, but worth to know. So, in summary, threads are required for this game, and that is a big downside. And there is one more thing. The right holder didn't allow the intellectual property to be shared publicly. So we decided to let users upload their own game resources and store them in indexed.db for fast access on the second launch. But, but as Sunware released this feature, we got a lot of hate because selecting files on mobile devices, especially Android, is a mess. Depending on the file manager, users may not be able to select zip files, some files may not show up, folder selection may not work, or multiple file selection may be disabled. There were a ton of issues. We solved this by allowing every possible upload method. Whatever way the user can provide the files, it is accepted. We even allowed uploading one file at a time. Once we did it, the hate stopped. IndexedDB turned out to be not so stable database, especially on Safari. If you try to store, say, 6 large files in a row, it often crashes on mobile Safari, and the only way to fix it is by reloading the page. Some users had to repeat the same upload process up to 20 times just to get all 6 files as stored successfully. Even on Chrome, we ran into a strange issue. For some users, after a few game sessions, Chrome would crash and its indexed DB storage would grow to several gigabytes, even though the game only saves around 200 megabytes. We opened an issue about this, but it hasn't been solved yet. Unfortunately, Chrome powers a lot of the browsers. The only browser that has worked perfectly so far is Firefox. No complaints from users there. To sum it up, the game actually had a great potential for porting, but due to the multi-threading and networking, we had to put in some real work. So in the end, it wasn't exactly easy, but not super hard either. It landed somewhere in the middle. Now you can see how, with a set of clear factors, you can quickly and fairly accurately assess how port-friendly a game is. I systematized all these points into a single table, and here is a link to it. And of course, you can always ask me directly. Here are links to the games you can play right now. Thank you.